Today we start section 3.1 and we are going to be moving on from the review of factoring that we did last time, and we're going to start talking about power functions and polynomial functions. Power functions we're going to use to help introduce us to polynomial functions, but we've seen some of these before, so let's take a look. A power function is a function that can be represented in the form of f of x equals x raised to the p power, where the base is a variable, that's the x part, and the exponent, p, is a positive integer. So we're going to see some characteristics of these types of functions. The first thing we want to consider is which of our toolkit functions are power functions. So let's go through these. First, and this one's kind of a unique one in the power function family, but we have the constant function. And the reason the constant function is actually a power function, and actually according to our definition, now that I think about it, it would not be, because the constant function is x to the 0 power, and we need our exponent to be a positive integer. So this one actually is not in the power function family. All right, this one is, because f of x equals x, that's x to the first power, and we want to take a look at that so we can see that we've got a line there, and that is also called our identity function. Then we can see we have x squared, x to the second power, so that is a positive integer in the exponent, and we can see that that one is also a shape that we've dealt with and we're going to continue dealing with in this chapter, but that is a parabola. Next we have f of x equals x cubed, and again we have x to a power, and what we're looking for in these situations is we're looking for what sort of characteristics do these things have that might be helpful to us as we investigate some of this stuff. So we're going to come back to them in a minute. All right, so now that we've gone through the pictures that we had, one thing we want to notice, and this is the question, what point or points do the toolkit functions have in common? So notice that we have this cubic function and the quadratic function and the linear function, and if you notice, and it's going to be, I can't really circle these very well on this because I'm switching screens, but every one of these functions is going to go through the point 0, 0, and 1, 1. So you can see that here on this picture. I'm going to go ahead and do it. So 0, 0 is going to be right here, and 1, 1 is going to be right there. So you can see that in the linear function. You can also see the 0, 0 and 1, 1 in the quadratic function. And lastly, we can see the 0, 0 and 1, 1 in the cubic function. And if you think about those numbers, an input of 0 and an input of 1, if you're just taking that function, that input value, and raising it to a power, those are always actually going to be points on our power functions. So that's going to be one thing that we kind of want to keep in mind. But another thing we want to keep in mind is just the general shape. So here's a picture of power functions that have even exponents. You can see the purple one is the x squared, the green one is the x to the 4th power, and the blue one is the x to the 6th power. And once again, as you look at these, you'll notice they all go through this point 0, 0, and they all go through this point 1, 1. And actually these have an additional point that they all go through, and that's the point -1, 1. But even more importantly, what we want to consider about these is that they all open up. Which means they're going up on the right-hand side of the graph and up on the left-hand side of the graph. And we're going to use that information to help us as we talk about polynomials. So we want to keep that in mind, make sure you make note of that. If it's an even exponent in the power function, On the left-hand side, the function will go up, and on the right-hand side, the function will go up. Now notice the difference. What happens when we have an odd exponent? For an odd exponent, once again, we still have this 0, 0, and 1, 1. And then this time, they both have a negative 1, negative 1. Or not both. Yeah, I guess, no, there's 3 of them there. They're just close together. So, but again, what's most important for us is that we want to notice in an odd degreed power function, these functions on the left and the right go opposite directions. So when we look at these, notice all of them go down on the left, but then they go up on the right. And again, we're not really talking about what's happening in the middle here, and we're going to see that in a little bit, but we can see that on the left-hand side of these graphs, these all go down, and on the right-hand side of the graphs, they all go up. So again, make note of that. Make sure you have that kind of marked down in your notes because we're going to be using that as we move on. Now, to move on to polynomial functions in general, we have a polynomial function of degree n, and that is a function that has this form. Now, I know this looks really complicated the first time you see it, but we're going to break it down and make it a little bit easier. The one thing that we have to note is n is a non-negative integer, and a sub n is not 0. So notice where the n is, that's the exponent for that very first term, and the a sub n is in front of the x raised to the nth power. Couple things we want to talk about here. All those a's are just numbers, and we call those numbers in front of the x's, we call those coefficients of the polynomial. So I know that's, again, very complicated looking. All it really says is you've got a number times x to a power, plus another number times x to a power, plus another number times x to a power, and so on, all the way until you get down to that last term, which is just a number. A term of a polynomial is any one piece of that sum, and so it's going to look like a number, a sub I, times x to a power. And that's what I was just talking about. Each one of those little pieces is called a term, and each one of them is just made up of a number times x to a power. Now here's where it starts getting, that's some terminology, but here's where it starts getting important to what we're going to be looking at. The degree of the polynomial is the highest power of the variable that occurs in the polynomial. So this is the highest power of the variable that occurs in the entire polynomial. Now when we write them, normally we put them in standard form, so the highest power would be the first one. But I know that some of the problems on the computer and some of the examples in the book, they are not in standard form. They don't go from highest power to lowest power. So you do have to be careful that you're paying attention and looking through the whole polynomial to see which one has the biggest exponent. Then we have what is called the leading term. And the leading term is the term that contains the highest power. So again, if it's written in standard form, that's this term right here at the beginning. That's going to be the leading term, and so it's the term with the highest degree. Then we have the leading coefficient, and the leading coefficient is just the coefficient of the leading term. And once again, if it's in standard form, our leading coefficient is this number that's in front of the x to the nth power. And we'll do some examples like this, but that's your leading coefficient and your leading term. For example 4, we want to identify the degree, the leading term, and the leading coefficient of these polynomials. Now, as I mentioned, you can just search and find your degree and your leading term and so on. My suggestion is going to be this. Let's take it and let's put it in standard form, because then it's really easy to find. So standard form would be we start with the term that has the highest power, which is right here. So negative 4x cubed should go first. And then the next one would be 2x squared, because that exponent is the next one, less than the 3, and then the only term that we have left is the plus 3. So biggest power goes first, and then we just go down through the powers until we get to the end of our number. So now, let's look at this and let's identify. And I'm going to switch colors here so I can circle things and point to things. So our degree. The degree of this function, remember the degree is just the highest power. So that's going to be this 3 right here. Our degree is 3. Next, we want to identify the leading term. So the leading term is the term that contains the highest powered exponent. And so that's going to be the negative 4x cubed. It's that whole term. Remember, a number times x to a power. And then finally, we have the leading coefficient. My eyes are not writing very well here. And the leading coefficient, remember, is just the number of that leading term, the number part, so negative 4. So that's our degree, our leading coefficient, and our leading term for that particular example. For example B here, notice this is already written in standard form, so I don't have to worry about rearranging anything. I am just going to go ahead and label the degree or identify the degree. I'm going to abbreviate these. That got too much writing. So the degree in this case is the highest exponent, and this is a 5. Then we go on to the leading term, so that's going to be my abbreviation for leading term. And the leading term, remember, is the term that contains that highest power. So that's going to be 5t to the 5th power. And then finally, our leading coefficient. So there's my abbreviation for leading coefficient. And that's just the number part of that leading term. And so that's going to be a 5. Lots of 5s in this one. But the first 5 is from the exponent. The second 5 is just part, well, it's part of the others are part of the terms, and then the leading coefficient is also a 5. Once again with C, I would go ahead and rearrange it. So the term that has the highest power is that p cubed, so we're going to have a negative p cubed at the beginning, and then we have plus 6p. One thing to remember is the sign stays with the term. So if you move the p cubed to the front, that negative goes with it. And then we have the minus 2 at the end. Just like the 6 is positive, so it stays positive even if we move it to the middle of that polynomial. So let's go ahead and identify. Once we put it in this order, it's pretty easy. The degree is this 3 right up here. So that's our degree of the polynomial. Then we have the leading term. And the leading term is that entire term, so negative p cubed. And then finally we have the, hang on, let me put a box around this like I have been. There's our leading term. Then we have our leading coefficient. And the leading coefficient, it's a little bit trickier this time. We just see a negative sign, but you have to remember what number is always in front of there. If we don't see anything, it's going to be a negative 1. So that's our leading coefficient, our leading term, and our degree. So pretty easy to identify those, especially if you put the polynomials in standard form. Now we're going to come back and we're going to kind of think about those power functions again. And the reason we're going to do that is because they give us some information about what we call end behavior of polynomials. And to discover or figure out the end behavior of a polynomial, we want to use something called the leading coefficient test. So when we do this, it's fairly easy because the end behavior of a polynomial is determined by the degree of the polynomial, which we have called n, and the sign of the leading coefficient, which is the number in the front of that term. So before we go on and actually get to what we're going to be to using this leading coefficient test, we want to get some notation done first. And so here's our notation that we're going to have as we look at this. We've seen infinities before. In this context, we're always going to be talking about the left side end behavior, so what happens on the far left side, and the right side end behavior. So notice we're always going to be dealing with x approaches negative infinity because we always want to know what happens on the left, and we're always going to have also x approaches positive infinity because we want to describe what happens on the right as well. Now if you go back and think about your power functions, only two things ever happened. The graph, the function, either went up or it went down. So the way we describe that is, if our function goes up, then the way we describe that is we would say f of x approaches infinity. In other words, those function values approach infinity, they get bigger and bigger and bigger in a positive direction. If our graph goes down, we would say the function values approach negative infinity. Okay, so when we're talking about left and right, we're dealing with x values. When we talk about up and down, that's the y values or the f of x values if we're using function notation. So that's something we want to pay attention to. We're going to be using these notations to help us describe the end behavior of our functions. So here is an example of an odd degreed function, and notice here it says that the coefficient is positive. So odd degree, coefficient's positive, and I know in your notes, maybe in your notes it's not quite as big of a space, but we're going to have 4 examples here, and you're going to want to write them down. Okay, so notice when we have an odd degree function, what happens is the graph goes down on the left and it goes up on the right. So this is how we describe that. As x approaches negative infinity, that means on the left-hand side, the x values are getting further and further negative. The y values, or the f of x values, are approaching negative infinity. They're going down. Then we go over here to the right-hand side. As x approaches positive infinity, that means we're talking about the right-hand side. The y values, or the function values, are increasing. They're going up, so y approaches infinity. Now, one thing I want to point out to you is, if we go back to all those odd degreed power functions that we had, if you remember what they kind of look like, and I can't remember if they're in your notes or not, the picture, but they all kind of look like this, and every one of them went down on the left, and every one of them went up on the right. Notice that is exactly what's happening here as far as our end behavior. Now, remember, we're not talking about the middle of the function at this point. We're just talking about the end behavior, what happens on the far left-hand side and what happens on the far right-hand side. So we can use these power functions in those pictures that we had, and again, I think they're in your notes, and if they're not, you probably want to go back and watch that again and write them down, but that's going to help us identify what happens in these polynomial functions. So let's go to the next one. And the next one is going to be an odd degreed function with a negative leading coefficient. Now, this is where we have to pull out some of our information that we've done earlier in the year. If we put a negative in front of a function, that reflects the function over the x-axis. So whatever was positive becomes negative, and whatever was negative becomes positive. So again, if we go back to our odd degreed power functions, which kind of looked like this, if we would reflect that, notice now it's going to look like this. So now it's going to be up on the left and down on the right. And notice that is exactly what we see in our picture here, and the reason is because now your leading coefficient is negative. Okay, so that reflects the graph. Now, again, I want to point out, as x approaches negative infinity, that means we're describing the left-hand side, and as x approaches positive infinity, that means you're describing the right-hand side. You are always going to have these two descriptions, because you are always going to describe what happens on the left and what happens on the right. And then the rest of it is obviously then this one is going up. We can see that up here. And this one down here we can see is going down. So the only part that changes is actually this very last either infinity or negative infinity. Everything else always stays the same because we're always talking about describing the function on the left and describing the function on the right. Let's go to our even degreed functions. So notice even degree, let's see, positive leading coefficient, and if we think about our power functions again, every one of them, some of them were, whoops, that didn't go down quite far enough, but anyway, they were all going, if you remember, they were going up on the left and up on the right, and notice that's what we see here, up on the left, up on the right, so that's following the same pattern. And then again, we're always going to describe what happens on the left, we're always going to describe what happens on the right, and that is our description there. Notice this time, because they're both going up, we have a positive infinity in this spot for both sides. Now, before I go on, whoops, I should have left that one there. I wanted to erase the rest of these. Let's see if we can predict what happens on the next one. We're going to have a negative leading coefficient. So instead of positive, it's going to be a negative. And the negatives we've just talked about reflect the graph. So hopefully you're kind of thinking through this. If we reflected this graph here, or our power function graphs, instead of them opening up on the left and up on the right, like they normally do, if they get reflected, they're going to end up looking like this. And we're going to notice they're going to be down on the left and down on the right if they are reflected. So let's go to the next slide and let's take a look at that. And yes, you can see it. Again, our picture was down on the left and down on the right. We can see down on the left right here. And we can see down on the right over here. And then again, just as we have every time, we're describing the left-hand side, we're describing the right-hand side. And since they're going down, negative infinity over here for the left and negative infinity over here for the right. So hopefully that kind of helps us, but kind of try to always relate yourself back to those pictures of your power functions. And remembering that the even degreed power functions always went both up normally, and then if they were reflected, they would both go down. And then remember that the odd degreed power functions always went opposite directions, down on the left and up on the right. But again, if it's reflected, then that switches. Let's do some examples. Now I think these are mostly the examples we did earlier, so I am once again going to start out by rearranging these and putting them in standard form so it's easier for us to think about this. Negative 4x cubed plus 2x squared plus 3. So we want to look at two things here. If you remember back a couple slides ago, we were always going to compare the degree. I'm going to use blue for that, the degree. And we were going to look at the leading coefficient. Leading coefficient. Okay, so our degree. First of all, our degree is a 3. Now the important part about that 3 is that it is odd. So if you're thinking about your power functions and the degree is odd, if you remember, that means the basic shape was like this. So a lot of times it was down on the left and up on the right, or if it was reflected, it could be up on the left and down on the right. So I'm just drawing arrows to help us picture this. I'm not drawing the whole graph. Actually, why don't I'll just draw it like this. Oops, that's not the erase. I'll just draw the shape. Okay, so our power function would look like this, and then if it was reflected, it would look like this. I don't know, hopefully that's better or whatever. So that's our two options, down on the left and up on the right, or up on the left and down on the right. Now the way we figure out which one is which is we go to our leading coefficient, which in this case is a negative 4. What's important about that is it is negative. And if it's negative, that means the function has been reflected, so it's going to be like this one over here. So it's going to be up on the left. So when we describe this, we're going to say as x approaches negative infinity, that means we're describing the left-hand side. The function approaches, since it's up, the function approaches infinity. And that is this one right here. Then we can see on the right, as x approaches infinity, the function is going down, so that's telling us negative infinity. So remember, the only thing that is changing is these two values. It's either going to be infinity or negative infinity, and in this case, that's what those are. For our next one, remember this one was already in standard form, so let's go to our degree right away. And the degree we can see is 5. And then we can go to our leading coefficient. And if you remember, that one was also 5, that leading coefficient was also 5. But let's talk about what these mean again. The degree, what's important there is it is odd. So just like the last one, it means it's like this power function or a reflected power function. And then once we know that our degree is our leading coefficient is a 5, what's important there is that is a positive leading coefficient. So that's just the normal version. It has not been reflected, it just stays like that. So in this case, we know that this is going to be down on the left, and it's going to be up on the right. So again, t approaches negative infinity is the left, t approaches positive infinity is going to be the right. And I always put them in that same order, so you're gonna see that. I think the computer program also puts it in that same order. Describe our end behavior here. Again, we talked about we need to rearrange, so let's go ahead and write this in standard form. So h of p, they're using other variables here besides just x's, and that's fine. H of p equals, and we had rearranged this to be negative p cubed plus 6p minus 2. So our degree is the exponent, so that's going to be 3. And once again, that is odd. Whoops, that doesn't say odd. Odd. So we've got, it's either going to look like this power function or like this power function. So I didn't do a very good job here giving us other examples because all of these were odd. Then we want to look at the leading coefficient. Leading coefficient is a -1. So that means it's negative, and that's the important part there. That means it's been reflected, and it's going to look like this. So if we look at the left-hand side, we can see that that graph is going up, so positive infinity. And when we look at the right-hand side, we can see that graph is going down, so negative infinity. All right, I want to go back because I don't know why I did this. I thought I had examples of each type. So I'm going to make a new function here, and I'm just going to put it in standard form right away. So let's say our function is p negative 2p to the 4th power minus 5p cubed plus 3p squared minus 7. So when we look at this, again, we look at our degree first, and we can see that our degree is 4 in this one that I've made up. And what's important there is it's even. And what that means is it's like our even degree power functions. It's going to go up on the left and up on the right, or down on the left and down on the right. And again, we're just relating these to the power function. It doesn't mean the whole graph looks like this. But then when we look at our leading coefficient, in this case we can see it's a -2, and since it's negative, it's been reflected, and that means it would be this one. So if we were describing this one, since it goes down on the left, we'd put negative infinity, and since it goes down on the right, we'd put negative infinity there as well. And so there's another example, but one that has an even degree. Example 5. What can we determine about the degree and the leading coefficient of this equation? Or of the polynomial that's graphed here, of the equation of the polynomial that's graphed. And so the two things we're looking at, we're just going to look at the end behavior. Notice it's down on the left and up on the right. So that looks like our power functions that kind of look like that, because you see down on the left and you see up on the right. So what type of power function was this one? If you don't remember, you can look back in your notes. But what we know is, since they go opposite directions, the degree is odd for this equation. And then the other thing we want to talk about is the leading coefficient. The leading coefficient is, so here's our question. Is it going to be positive or is it going to be negative? Well, we have to ask ourselves, does this power function, has it been reflected to look like this blue graph, or has it not been? And it has not been, so we know that our leading coefficient is positive. Okay, so we can look at an equation and figure out about the graph, or in this case we're able to look at the graph and figure out some things about the equation. So we know that the degree is odd because the end behavior goes opposite directions, and then since it's down on the left and up on the right, we know that is a positive leading coefficient. All right, when we look at our graphs, we also want to talk about horizontal intercepts. Those horizontal intercepts where it crosses usually the x-axis are also called zeros of the function or roots of the function. So in example 6 here, we're given the polynomial function, and notice it is already factored so that we don't have to worry about factoring it. We are going to keep practicing that, but for now it's already factored for us. We want to determine the vertical and horizontal intercepts. So here's how we're going to do that. We're going to start out with the horizontal intercepts. And I think I'm going to do that in blue, so let me change colors there. Okay. To find the horizontal intercepts, what we're going to do is we set the entire function equal to 0. So here's what we're going to do. F of x equals 0, or whatever the function is called. So that would say 0 equals x minus 2 times x plus 1 times x minus 4. And we actually talked about this when we were at the very end of our review of factoring. This one's already factored and equals 0. The way we solve this is we just take each individual factor and set it equal to 0, because if x minus 2 equals 0, that entire product will end up being 0. If x plus 1 equals 0, the entire product will equal 0. And also if x minus 4 equals 0, the entire product will be 0. So then we solve, add 2, and we're going to get x, oh hang on, let me go back and use blue. So we get x equals 2, and we're looking for intercepts, so we're going to put 2 comma 0 is going to be one of them. The next one, we're going to subtract 1. So we get x equals 1, and that means that our intercept is going to be 1 comma 0. Oh wait, sorry, that's not right. Back up. Since we subtracted 1, it should be x equals negative 1. That gives us negative 1 comma 0 as our second intercept. And then our third intercept here, we're going to add 4. And when we add 4, we get x equals 4. So our third intercept is 4 comma 0. Now those are all, whoops, why am I not putting these in parentheses? I'm getting distracted because my daughter just came down and looked in the room. Okay, so they're in parentheses. Those are all horizontal intercepts. That's how we find the horizontal intercepts. To find the vertical intercepts, let's switch colors here. Vertical intercepts, they're actually easier. To find the vertical intercepts, we just take the x and replace all the x's with zeros, just like we replaced the f of x with a 0 for the other one. So here's what that turns into. It turns into finding f of 0, and that will be 0 minus 2, and 0 plus 1, and 0 minus 4. And you can see why this becomes pretty easy, because 0 minus 2 is negative 2, 0 plus 1 is 1, and 0 minus 4 is negative 4. And then remember, these are in parentheses. They're all multiplied together. So negative 2 times 1 times negative 4 is going to be positive 8. So that means our ordered pair there for the vertical intercept is going to be 0, 8. So that's how we find the horizontal and the vertical intercepts. And you always do those the same way regardless of what type of function. So if you ever need to find the horizontal intercepts, you just replace the function, the f of x or the g of x or whatever, with a 0. If you're going to find the vertical intercepts, you always replace the x or whatever variable they're using with a 0. So some pieces of information about these polynomial functions. If your polynomial function has a degree of n, here's what will be true. And that n should be italicized. I don't know why it's not. Need to fix that. If the degree is n, then there can be at most n number of horizontal intercepts. So that example we just did where we found 3 horizontal intercepts, that means the degree of that function has to be at least 3, because if the degree is 3, it can have at most 3 horizontal intercepts. We also know that an odd degree polynomial will always have at least 1 horizontal intercept. If it's an even degree, if you think about that shape, it could be that here's our x-axis, and it could be that the function is either completely above the x-axis or maybe an opening up, or completely below the x-axis and open down. So it doesn't have to have a horizontal intercept if it's an even degree. But if it's an odd degree, if you think about what that looked like, something like this, no matter where you draw it, it's always going up and down, so it's always going to cross here sometime. So that's what that part is about. The other thing is that if the function has a degree of n, it will have at most n minus 1 turning points. And when we talk about turning points, we're talking about things like this. This would be a turning point, and this would be a turning point. So if that has 2, we'll call them turning points, I'm going to abbreviate, 2 turning points, the degree has to be at least, is at least 3. Come on. Okay, because the degree has to be 1 more than that, or this has to be 1 less than this. So there's different ways of thinking about that, but we're going to do some examples like those as well. Looking at this one, what can we conclude about the degree of the polynomial shown? So the first thing that I would probably always look at is how many intercepts does it have? So by looking at the intercepts, it has 2 intercepts, so we would start out saying, okay, I know my degree has to be at least 2 because it has 2 intercepts. But then we also want to consider the turning points. So notice we have 1, 2, 3 turning points. So that tells us, nope, it's not at least 2. It has to have at least a degree of 4. Okay, because the turning points always have to be 1 less than the degree, or at least 1 less than the degree. So if you've got 3 turning points, your degree is at least 4. And then the other thing, if we really wanted to, we could go back and we could say, and we know it's even because the end behavior, they're both going up. So we also know the degree is even. So several things we can get from there. We know it's at least 4 and it's even for this particular graph. And that's the end of section 3.1. You've got 7 problems to do there, so take your time on those. And again, if you have questions, please feel free to email me or ask them. I know some of you are working with some other people to get some tutoring, and that's fine, but don't be afraid to ask me for help if you need some help with something.